a little more in depth and significant figures. So we're going to use dimensional analysis to convert from units to units. To do that, what we're going to do is we're going to locate our conversion factor. And a conversion factor, it can simply be written as a ratio. So if I know that 1 inch is 2.54 centimeters, then I can take 1 inch to every 2.54 centimeters, or 2.54 centimeters to every 1 inch. So I can use dimensional analysis to determine how many centimeters are in 6.5 inches. I'm going to start with 6.5 inches, and then I'm going to multiply it by the correct ratio that gets rid of inches and gives me centimeters. So since inches is up top here, I need the ratio that has inches on the bottom. So one of the most common mistakes is that people get their units lined up right, but they'll switch their numbers. So be careful and make sure that you have a 1 beside inches and a 2.54 beside centimeters. And notice that the inches cancel out. So if I take 6.25 and I multiply it by 2.54, then I get 16.51 or 16.5 centimeters. Likewise, I could do this with more complicated units. I could take meters per second, and I can look up, and I could turn it into miles per hour. So if I have 60 miles per hour, I want to pick the right ratio to convert to meters per second. So I want whatever the number is beside meters per second up top, and I want miles per hour on the bottom. Well, it's 1 mile per hour for every 0.447 meters per second. So I'm going to multiply 60 times 0.447. I get 26.82 or 26.8 meters per second. So let's do an example where we convert 60 meters per second to miles per hour. So we're going to start with 60 meters per second over 1. And we're going to find the conversion for that. 1 to 0.447. And this time we're going to put meters per second on the bottom to cancel out what's up top. So we'll put 447 on the bottom to 1 mile per hour. So now we're going to divide 60 divided by 0.447, and we're going to get 134 miles per hour. Now, let's talk about how we know when to round and where we round. And that has to do with the fact that we're dealing with measured values in these problems. And so let's consider using a ruler to measure. So this is a typical metric ruler, and you notice that the smallest division is a millimeter. So that's not these numbers. That's actually what each one of these little teeny lines is. Each line is 1 millimeter. Okay? So let's say that we have a line and we're going to measure the length of it. Well, it's pretty clear cut that if we measure a line that goes to this number here, it's right on 4 centimeters. So we know the answer is 4 centimeters, but how many decimal places can that have? Well, we know that the smallest division is 1 millimeter, or 1/10 of a centimeter. So each one of these little lines here is going up by 1/10. So if it had landed on the line after 4, it would have been 4.1, 4.2, 4.3, 4.4, 4.5, 0.6, 0.7, 0.8, 0.9, 5. It's going up by that. So the smallest division is 1/10 of a millimeter. So we know for sure that we can go out to the smallest thing. But can we go any further? Well, let's consider another option. Let's say that we have a measurement that lands between 2 lines. So let's say that it lands right here between 2 lines. So our eyes are not really super awesome. I mean, they're great, but they can't resolve this into specifically where we are between the 5 and the 5.1. We know we're somewhere between 5.0 and 5.1, but are we anywhere else? Are we at 5.11 or 5.12? The only way to know that would be to have another scale that blew this up and gave us another scale division that took each millimeter and blew it up into tenths. And we don't have that. But we can estimate safely to the second place. We can say whether it's 5.0 or 5.05 or 5.10, right? We can definitely go to half of that smallest division. So that means that we can estimate out to some degree to the second place. So when we use a metric ruler, this is going to have 3 decimal places. That last decimal place is an estimated place, and it's dependent on the smallest division as to how far out we can go. We can't go to the nearest 1/100th of a centimeter, but we can go to 4.00 plus or minus 0.05, right, centimeters. So we could have an answer that was 3.95 or 4.05 or 4.00. This is called the uncertainty of the measurement. And we always need to be able to find that uncertainty when we use a measured value. And it's really easy to do. The rule of thumb is that you figure out what the smallest division is, which is 1 millimeter. And I'm going to change that to centimeters because I'm using the centimeter scale here. So 1 millimeter is 0.1 of a centimeter. And then I just divide it in half. And half of 0.1 is 0.05. So that is our uncertainty in our values. And so all our measured values, even if they're dead on even, like the one that was on 4 centimeters, should have 2 decimal places because these are significant in the measurement itself. So the rule of thumb is to find the uncertainty, which is the degree to which you can estimate a measurement, which tells you how precise that measurement is. It's also called the tolerance of the device, is take the smallest division and divide it by 2. So our smallest division is 0.1 centimeters. We divide it by 2 is 0.05. So any of our measurements will have 2 decimal places. And the error, the uncertainty of that measurement place is plus or minus 0.05, or the tolerance or uncertainty of the measurement, centimeters. We can't do that for every value. And we're going to talk about a way to do that using significant figures, because that's going to affect when we start putting all these measured values into equations. We got to know where to round. It all has to do with the precision of the measured values that you've used. The other thing that we also look at is how accurate our values are, and accuracy is how close you are to the actual measurement. And to do that in class, we usually find the percent error. We take the experimental value and then we take the real value and we divide it by the real value. So an example would be finding pi. Maybe in lab, you found it to be 3.12. But in your calculator, the actual value is pi on your calculator, right? Which is 3.1214, blah, 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 blah. It keeps going. So if I were to find that, I would just take the absolute value of my 3.12 minus real pi, divide it by pi, and then times 100% to make it a percent. If I do that, I get 3.12 minus pi equals, divide that by pi, equals, and then times 100. So that would be 0.69% error. So I was off, plus or minus 0.69. It was really a negative number. I was low by 0.69% of what pi really is. So let's talk about what it means to be precise and what it means to be accurate. Accurate means that you're close to the real value. And precise means that your measurements are repeatable, which happens when you have a small uncertainty or tolerance. So let's look at these graphs. So if you are precise and accurate, so imagine this is a dartboard. If you're precise, that means that every time you throw the dot, you get in, you're very close. You're always hitting the same mark or very close to the same mark. You have a tight grouping. And if you're accurate and you're aiming for the bullseye, then your grouping would be right on the bullseye. So this A is precise and accurate. In B, you've missed the bullseye, so you're not accurate, but you are just precise. And in C, you're accurate, but not precise, right? Because you don't have a tight grouping. And in D, you're not accurate or precise. So how do we keep track of this in our and when we're doing measurements? How do we keep track of our uncertainty? Well, it's pretty easy. We count significant digits. That's kind of a quick and dirty way of figuring out how precise a value is. And the rules are, if you're a non-zero number, like 1, 2, 3, 4, 5, then you're significant. So the number 2, 1, 3, 5 has 4 significant digits or figures. And if there's zeros between those numbers, they're significant. So if it was 2, 0, 1, 3, 5, now you have 5 significant digits. And if you had zeros to the right of the decimal, at the end of the decimal, you don't write those for no reason. Just like when we made measurements with the ruler, we added those 2 zeros because our uncertainty went out that far. So 2.00 has 3 significant digits, but if the zeros are before the decimal point, they are not significant. So these are not significant. And one way to test that is if you put this in scientific notation, it would be 2.00 e to the negative 3. So that e to the negative 3 means those zeros are just placeholders, and there are only 3 significant digits in the measurement. So one way to really determine whether those zeros are significant or not is to see if they get turned into an exponent. And if they do, they're not significant. Let's look at some examples here. 5.03. The 5 and the 3 are significant, and the zeros between them. So there's 3 sigdigs. Here's one that's commonly mistaken. 0.002. If I put this in scientific notation, this would be 2e to the negative 3. So there's only 1 sigdig. 2.00 centimeters. Those zeros at the end of the decimal are significant, so there's 3. And 2, 6, there are no zeros to worry about. 2, 6 has 2 sig digs. If I am wanting to round, remember that what you do is you look at, we want 2 significant digits, so you look at it the third digit place, and if it's 5 or higher, you're going to round up. So 2.3, that would be 2 sig digs. 4 is lower than 5, so it's going to be 2.3 centimeters. 3.96, 3 is the first significant digit, 9 is the second significant digit, 6 is higher than 5, so that's going to round up to 10, which is going to carry over. This will be 0.40 centimeters. And then 1.99, 1.9 is going to round up to 2.0 centimeters. We don't want to drop that 0 on either of those last two because those are placeholders holding the precision. And finally, we need to have some rules because in our formulas, we're adding and subtracting and multiplying and dividing. And the rule is that when you're working with measured quantities, the answer should never be more precise than the least precise measurement. So for adding and subtracting, since you add and subtract like things, like you add distances or you subtract distances, they are being measured with similar tools. So you can just actually measure the precision by decimals. For example, 2.00 plus 3, the least precise value is 3. So when you add those together, your answer will be 5 and you'll have no decimal places. Your answer can be no more precise than the least precise value. When you multiply and divide, now you're dealing with quantities of different, that are made with different measuring devices. And so you can't really compare decimals because they're totally different measuring devices. So you have to count significant figures. So let's say that I am going to multiply 40.0 meters per second by 2 seconds. Actually, 2.0 seconds. The least number of sig digs are, this has 3 and this has 2. So my answer has to have 2 significant digits. Well, 2 times 40 is 80, and 80 is 2 significant digits. And that would turn out to be meters. Notice that I am writing my units all the time for the answers, and I expect you guys to do that as well. What if this had been 40.0 meters per second times 0.002? Okay, so this would have been 80 thousandths, which would be 0.080 would be my answer. But how many significant digits? Well, right now I have 3 significant digits. But remember, 0.002 only has 1 sig dig. So I should really only have this answer go to 0.08 meters. So here's an example for you to do. Let's say that you're finding the acceleration of an object, which is the final velocity minus the initial velocity all over the total time. Let's say that the car goes from 0 meters per second to negative 20 meters per second in 2 seconds. And let's put some significant digits in here. So let's say that this is 2.00 seconds and 20.0 meters per second. How many significant digits does 20 have? Well, it's got 3. And how many significant digits does 2 have? It has 3 as well. So when I plug in my numbers, the rule is that you always round. Use your, whatever the last operation you did is the rule that you use. So in this particular example, I'm not going to round it all until I divide by time. So this is going to be final velocity is negative 20.0 meters per second minus 0 all over 2.00 seconds. So that's going to be negative 20.0 meters per second divided by 2.00 seconds. My acceleration is going to be negative 10.0 meters per second squared. Notice that this has 3 sig digs and this has 3 sig digs. And the rule is my answer can't be any more precise than the least precise. Well, they both have the same number, so I'm going to have 3 significant digits. And notice too that I modeled for you how to show your units in that problem. You're going to substitute in your values with the units, and then you're going to use dimensional analysis to determine the units of the new object, of the new quantity.